Hi, this is Jeremy, one of the authors of the textbook Machine Learning Refined. In this short video, I'm going to give a walkthrough of one of the Jupyter notebooks in our GitHub repo that is titled 6.2 Neural Network Space Warp Demo. Now, there are several ways for you to get your hands on the content of this repo. You can clone it as you would any other GitHub repo, or you can launch a live instance of the repo, or pull a Docker image containing all of its contents. That's what I'm going to do now. I've already opened up my Docker image of this GitHub repo. There it is. There's the notebook we'll be looking at today. I've opened that up in this tab. This notebook contains several interactive demonstrations that show you how a kernel or a neural network warps the underlying space of a data set. In particular, it shows you how a kernel or neural network transforms a two-class classification data set. In finding the nonlinear boundary that separates two classes, both of these algorithms essentially transform the data set into a space so that that data is separated by a line or hyperplane. What's especially cool about these demos is that you can actually define the kernel and neural network rules however you want and watch a variety of different transformations take place. So let's get started. We first import the required libraries. In the first demo here, space warping with a kernel, this Python cell creates a toy data set. A toy data set created by two polynomial kernel equations. Those are given here. You can change these however you want and see different kinds of transformations take place. In any case, these two rules define a circle in the classification space. Using that circle, we create a toy data set, two classes, red and green. The next Python cell creates a slider. As we slide from left to right, you'll see space warping. What's happening is space is warping from the original data space to what's called the transformed feature space, where each axis is defined by one of those rules we've given above. This slider mechanism shows you how when a kernel finds a nonlinear boundary in some original space, it is simultaneously transforming the data to what's called the feature transform space, where that data is separable by a line. And you can go back and forth, transforming the data from the original space on the left to the transformed feature space on the right. If you want to see both the original and transformed spaces simultaneously, you can activate this next cell here, and that will give you the original space in the left panel and the transformed space on the right. Now, if you want to check out more technical details about how these two spaces are related, check out Chapter 4 of our book. It's free for download on the website at mlrefined.com. Just click on Download Chapters. And right here, it's Chapter 4, Knowledge-Driven Classification. If you click on this, you can read all about original and transformed feature spaces in this chapter. Now back to the demo. As I mentioned here, you can change around these kernel rules however you want and watch different transformations take place. So, for example, I'll replace rule 2 here. Instead of squaring the second coordinate, I'll just leave it as the second coordinate, just plain. Let's see what happens. Rerunning this demo, first we have to produce the set of slides. And here's what the nonlinear boundary looks like. It looks parabolic. Running the slider mechanism below, we can then see how the transformation from original to transform feature space takes place. So sliding from left to right, we can see the underlying space warping, and we're transforming from the original space to the transformed feature space, where that nonlinear separation becomes linear. Then you can slide back and forth from transformed to original space, however you like. If you want to see the original and transformed feature spaces together in one slide, just activate the next cell, and there's the original and transformed feature space. All right, the next demo, we warp the space using neural nets. The only difference, thematically, from what we've seen above is how we define the rules. With the kernel example above, we used a polynomial kernel. Here we're going to use a neural network basis, and in particular one that employs tanh activation functions. So we have the two rules defined here. When we activate this cell, a set of slides are created, and in particular, with these set of rules, this nonlinear boundary is created along with the toy data set. When you activate the Python cell that follows, you create a slider that allows you to smoothly transition from the original space to the transformed feature space defined by these two neural network basis functions. So you're going to see here as we slide from left to right from the original space to the transformed space, because the neural net basis elements are defined as a composition of functions, that the transformation or the warping of the space will get much crazier than with the kernels. So we're pinching, we flip around, and there we are. Now this zigzag thing is a line. It's just that we can't plot a line very easily because of the way the space has been warped and stretched due to these two nonlinear rules, but this is a line. Now, just like before, you can go back and forth from the transform to original space and play around with this as much as you like. If you want to see the original and transform spaces, you can activate the next cell. So now you can see in the transform space, this is indeed a line. But here is your original space, and there's your transformed space as well. That's it for this demo. Thanks for viewing. If you want to find this Jupyter notebook as well as others with similar kinds of interactive demos, be sure to visit our GitHub repo. You can find a link to that repo in the description of this video. And if you want to read more about the technical details of how these machine learning algorithms work, check out our book. This is our homepage, mlrefined.com.